Welcome to the Science for the Public lecture series. Science for the Public is an organization committed to bringing science information and issues to the general public. Visit our website for our program listings and blog.
Good evening. I'm Yvonne Stapp for Science for the Public, and I welcome you to Contemporary Science Issues and Innovations. Tonight, we talk with Priyamvada Natarajan, professor of both astronomy and physics at Yale University. She'll be discussing her new book, Mapping the Heavens, also her cutting-edge research in astrophysics. In addition to her academic position as a theoretical astrophysicist at Yale, Dr. Natarajan also currently holds the Sophie and Tycho Brahe Professorship of the Dark Cosmology Center at the Niels Bohr Institute, University of Copenhagen. Her list of distinctions is long, so we refer you to her website or to her event page on our website. But we should mention that Dr. Natarajan is an elected fellow of the American Physical Society and that she was also elected to an honorary professorship for life at the University of Delhi, India. Dr. Natarajan's research focus includes dark matter maps of galaxy clusters, gravitational lensing, and the history of black holes over cosmic time, including the formation of the first black holes. She's also committed to communicating science to the general public. This commitment is reflected in her articles in New York Review of Books, and most especially in her splendid book, Mapping the Heavens, the Radical Scientific Ideas that Reveal the Cosmos. This book illustrates so well the difficult path of most breakthroughs in astronomy and cosmology, from resistance to acceptance, often a very long transition. We're delighted for the opportunity to talk about Dr. Natarajan's book and her own exciting research in astrophysics. We're very honored to welcome her tonight. Welcome.
Thank you. A real pleasure to be here.
And I'm going to ask to start with talking about your book. One of the best things about the book is it shows the fits and starts of introducing radical new ideas. Most of them were sort of rejected initially in astronomy. Is that true?
Absolutely. And I think part of what I wanted to show in the book, illustrate through these examples of many of the radical ideas that we take for granted today. The existence of dark matter, of black holes, the fact that the universe is not just expanding, but the expansion is accelerating. All of the things we take as a given at this point. But the process by which these ideas were first proposed, they were contested, and how they were eventually accepted is kind of complicated. But it's a complication, and in that complication, you actually see many wonderful aspects, sort of the human side of science. The fact that scientists are human, and science is a human endeavor. And so you have the passions of the scientists, jealousies, ambitions, and personality clashes that kind of play out in the process. And it's also true that the process of acceptance is extremely nonlinear. So some ideas you would imagine are so much more complex that they would have taken a much longer time to get accepted. But then you see it is the interplay of ideas and instruments. So it's science. So the ultimate arbiter is data. So when you have overwhelming evidence in support of an idea, then as scientists, first of all, we are trained to think and to reason, and therefore you cannot but be persuaded by the evidence. So, I mean, ultimately it's, instruments and ideas that really help us shift our thinking.
In terms of these ideas that met with resistance to begin with, do you have any big favorites that?
Well, since my own work centers principally on trying to understand the nature of dark matter by actually mapping it, and the origin and the growth history of black holes, I have to say the idea of dark matter, the existence of dark matter, and that of black holes are sort of two of my favorites. And also they illustrate sort of very different ways in which science works. So for example, the idea of a black hole originated from a mathematical solution. So it was an elegant mathematical solution, slightly perverse mathematical solution. And so it was not believed to correspond to anything real. So it was never believed for a long time, for almost 30, 40 years, that you could actually have a real astrophysical object that would be a black hole. It was a mathematical solution. So it started from a theoretical idea, and then eventually we found them and so on, right? But in the case of dark matter, it's entirely the opposite. There was no theoretical conception of dark matter. It was found in the data, evidence was found in the data. And then sort of a theoretical edifice sort of was built around it, and it turns out now that this theoretical idea of dark matter is fundamental to our conception of how structure forms in the universe.
Let me get something clarified here. I think most people know that our baryonic matter, the stuff that's all around us that we do perceive, is minuscule in the universe, but it's still a hard thing to get your head around. That's about 4% or something?
That's right.
And dark matter, that stuff we can't.
It's about 26% of the overall sort of mass energy inventory of the universe, and 90% or more of the total matter content. So the ordinary atoms, baryons that are anything in the periodic table, even the most, the biggest, most massive elements, the biggest atoms in the periodic table, they constitute 4%. And by and large, we know that because the majority of baryonic matter in the universe is hydrogen and helium, we actually know right after the Big Bang, after the first 3 minutes, we know how much was actually made. Because all the other elements are synthesized in the centers of stars. That happens over much later cosmic times. So, we have it's remarkable, but that we do have a really good inventory of everything in the universe. Well, all the matter anyway.
So that's amazing.
Although we don't know what dark matter is made of.
That's true.
Right. So we don't know what the particle is. We know it must have, formed sometime very early in the universe, and that it is copious and that it's smeared everywhere, but we don't know what it is.
On that, you mentioned that there's clumpy and smooth. You have two varieties, and I had never heard that before. How do you determine that it's
right? So it turns out that because dark matter forms the scaffolding in which all structure in the universe, including the galaxies and the stars in the galaxies, form, the dark matter is distributed in the universe. Because gravity is the only force that's felt by dark matter, they don't interact with any other forces. They're not electrically charged, these dark matter particles. So all the dark matter interacts by the force of its own gravity. So it flows in the universe. So it actually flows in sort of these filamentary structures in the universe. And what we find from our current understanding of galaxy formation is that dark matter is smeared very smoothly pretty much everywhere. But there are regions where you have these flows, these filaments, and those filaments intersect, where you have a lot of clumpiness. So you have a lot of concentration of dark matter. So the way to think about it is, because gravity is the only force in town, when you have a small, overdense sort of concentration of dark matter, it tends to grow, because gravity will pull in more stuff, and it will tend to grow. And this region that starts out having a little bit of an excess of dark matter over time progressively becomes really overdense in dark matter. But those regions are very interesting, because those are the very regions where galaxies end up forming.
And that was sort of determined at the very early stages of the universe.
Yes.
Sort of.
Yeah. These fluctuations were set up in the dark matter. So there was, you can think of it as a sea of dark matter with some very tiny fluctuations that got amplified over time.
So we look forward to learning what that is eventually. But you do think it's a particle?
Absolutely.
Okay. That's
so there. There was a proposal that to circumvent the idea that it was actually a particle, because we've not found it yet, right? And this idea was is referred to as modified Newtonian dynamics. And there the proposal is that it's not a particle, but it's just that the Newtonian force law, the force of gravitation, the 1/r² law, is actually slightly different on cosmic scales. And so that was a proposal, but it turns out that that alternative model to replace dark matter doesn't work.
Okay. So you're looking for
We're really looking for a particle.
And I hear more and more cold dark matter. And so that's
so these are very slow particles that don't interact.
Massive.
Yeah, massive. They don't interact with each other or with anything, basically.
It will be fascinating to learn more about that. And in terms of these ideas meeting with resistance, sometimes for very long periods, could you give us some examples of that?
Right. So I think that, part of the normal process of science is being open-minded and to contest ideas. So that's part of the method of science, right? However, when some really radical ideas are proposed, over and beyond the normal contestation, which is part and parcel of the intellectual process of science, you have individual personalities and you have their egos, you have their ambitions, which get involved in it. So I think, one of the cases that is particularly interesting is the discovery, the observational discovery of dark matter. So first of all, it is such a radical idea that it was discovered and then forgotten and then rediscovered many times. So Fritz Zwicky, who was this cantankerous Swiss astronomer who was at Caltech, right? He was brilliant. So he came up with the idea of dark matter by looking at the motions of galaxies in these distant objects that are called clusters. So it turns out we now know that clusters are the largest repositories of dark matter in the universe, and therefore the motions of galaxies that are bound in clusters, there are about 1,000 galaxies that are bound by the gravity of that dark matter. They are whizzing around much faster than they would if there was no further unseen matter. And Zwicky managed to measure the speeds of these galaxies and noticed that they could not be reconciled with all that we see. And so he proposed this idea of Dunkel materie, some dark matter that's invisible, right? And this was 1933. It was not taken as seriously. And then in 1937, he further noticed that if you do have such a large concentration of dark matter, as per Einstein's predictions from the theory of general relativity, that the presence of mass is going to deflect light, he said these regions of the sky should actually be huge light deflectors, and that and therefore they would be these gravitational lenses, and that we should be able to see sort of deformed shapes of background distant galaxies when we view the universe through these clusters, through regions where you have these clusters. And he predicted that, right, in 1937, and that was not taken seriously either. In fact, the first observation of a gravitational lens, which was confirmed, a cluster lens, was 1987.
So
there
very
was
late.
Right. So the deflection per se was detected already by when Einstein proposed the idea, which is the famous solar eclipse experiment expedition that was made in 1919 that proved the theory of general relativity. But the deflection of light by these massive objects at cosmic distances, well beyond our solar system, right? That the first discovery of that was multiple images of a quasar, and that was in the 60s. But the actual deflection of light by clusters of galaxies, which is the most dramatic thing that you can see, that happened only in 1987.
So it took 50 years
It almost 50 years.
Amazing.
Yeah.
Amazing.
Yeah.
Of course, he was not the kind of a person who would be embarrassed.
No, not at all. But I think the other interesting twist in the story is that dark matter, as I mentioned, is everywhere. So it's distributed not just in clusters of galaxies, but also in galaxies. So individual galaxies like our own have a big halo of dark matter that extends well beyond where the light is. And so in the 1970s, Vera Rubin and Kent Ford, they actually measured the speeds of stars in galaxies, spiral galaxies in particular, from the center outward. And once again, like Zwicky found, she found that they were moving around much faster, indicating there was something else that was contributing to gravity that was unseen. But they made these measurements in the early 70s, and it was such a radical claim that they actually just sat on the data for a few years before they actually published. So and it turns out finally they published it, and simultaneously they were talking about these results, but they were very cautious in claiming that there was this new sort of invisible entity, because invisible entities have a very checkered history, right? There was ether
back to the ether
that evaporated, right?
Exactly,
the idea of ether. So, but then what happened was they were talking about their findings at meetings. And simultaneously, theorists, Peebles, Yale, and Oestreicher, were noticing that, in fact, for the stability of galaxies, to understand why galaxies are stable in an expanding universe, they put forward the claim that it's dark matter, the halo of dark matter, that actually stabilizes galaxies. So slowly, the theoretical support for the idea and the theoretical need for that idea and the accommodation started. And so when that convergence happened, right, then the idea was really accepted.
But it's amazing that these are all central to modern astronomy.
Absolutely.
One after the other. In your book, this is just a...
the last 100 years have been incredible.
Yes.
And I think it is really the growth in technology, both with instruments and cameras and capabilities, our ability to launch satellites and to circumvent the Earth's atmosphere, as well as build very large telescopes on Earth, and computing.
Yes.
I think it's
very
these
important,
three things converging that have really made a huge difference.
Yes. I want to ask you about that, about the technology. I have one real quick question first about the delusions and so on. Can you give us an example of a situation where people saw things that were not there? I was thinking of Lowell, but there are other people that...
No, I think the case of Lowell is very, very interesting because, right, so the canals on Mars. Right, so Schiaparelli earlier, sort of imagined that they were there. But, one of the interesting things is how our imagination goes beyond in interpreting what is seen. There's always interpretation. When you see something, a distant object, you look through a telescope, you're obviously, this is the beautiful thing in cosmology, right? You never do controlled experiments. So it's not like, you have a microscopic plate and you can manipulate your specimen and then see what happens. What you see is what you get. So there you are, and there's a layer of interpretation. And the desire to discover the possibility of life elsewhere, the possibility of water on Mars, was just such a strong driver that you could see that they were, Lowell particularly was very excited at the possibility and really believed that we may not be the only intelligent beings on Earth. I mean, in a way, I'm fascinated by people like him because of the humility to not think that we are the only intelligent species on Earth. However, it was unsubstantiated. But what has come full circle now, right, is that we think there is evidence for ancient water on Mars. So,
ancient water.
Ancient water. It's not currently in liquid form. But the fact that the rover Curiosity is finding evidence, I think it's kind of coming nice full circle, right?
On that, though, there are astronomers or physicists who maintain this idea of life out there, and other people who don't. Where do you fall in this?
So I mean, I think that I think it serves to remind us that Copernicus really got us started by moving the pivot away from us, right? And I think it was the beginning of what has now culminated in this incredible revolution of understanding our place in the cosmos and the realization with the discovery of thousands of planets around nearby stars, right? So now we think that there are actually more planets than there are actually stars in the universe, right? Because you can have stars that have multiple planetary systems around them, right? And the fact that statistically, with such a large number of possible worlds, and many that we think are probably habitable,
Right.
given our understanding of life and the possibilities for life and its origin. I definitely believe that there could be life elsewhere. I mean, the thing that I am sort of tickled by is that it's quite possible that life as we know it might not, what turns up might not be recognizable to us as life forms. Because I remember Stephen Jay Gould famously said, right, even if we replay the tape of evolution on Earth,
yes.
it's unlikely that we would be the end products,
so
right?
true, right?
So I think, I believe that there are definitely life forms, whether they are anything like us, recognizable to us, or intelligent in the ways that we have come to define intelligence is an open question.
Exactly.
Completely
But
open
it's
question.
interesting how this has shifted. It wasn't very long ago when people that went looking for exoplanets were told your career is over if you try this. There's
Right.
just nothing out there. And now look, and it's changing very rapidly.
absolutely.
Absolutely. I'd like to switch to your work, which is this very cutting edge material, and you have diverse focuses in this regard. Can I start with the black holes, the early black holes? This seems to be full of, I don't know, controversy, a lot of difficulty. Can you give us some background?
Yeah, so I think what is intriguing about the early black holes is the seeds. Where do they come from? Where did the first black? So now we know that every galaxy, including our own, appears to have a supermassive black hole, which is 1,000,000 times the mass of the sun, that's sitting right at the center. And the question is, how did a black hole start out as a seed? What was the mass of the seed? How early in the universe did you have to form that seed in order to end up with this kind of population at the end of it, right? So one thing we know is that black holes can either be active or dead. Mm-hmm. And they're active when they're feasting on gas and growing and emitting in the process because of the way gas siphons onto them. As the gas is falling onto them, it gets heated up, and we see it in the X-ray. And those feeding black holes are called quasars. So these are very, very bright. And so these quasars actually outshine the stars in the entire galaxy. So we can see them out to great cosmic distances. In fact, the most distant objects in the universe that we've detected so far tend to be quasars. So what we have now found is that we find a population of extremely bright quasars that are in existence when the universe was 7% of its current age, a fraction of its current age, right? And the traditional thinking was that the way you make the first black hole seeds is that you make the first star, which then exhausts all its fuel, explodes, and leaves behind a little seed black hole. And then that seed consumes all this gas and sort of eventually builds up.
I see.
But the problem is that these bright quasars appear to be powered by black holes that are 1,000,000,000 times the mass of the sun when the universe was 7% of its current age. So how do you grow a tiny, wimpy little black hole seed, so rapidly in the universe? So there's a timing problem. There's a bit of a timing crunch.
Right.
Even if we overfeed black holes, there's a timing problem.
Well, you'd have to have huge stars too.
You'd have huge stars, or you'd have to have a very steady supply of gas that would be constantly feeding into the black hole. So you have this sort of, rapid feasting, sort of making these very obese black holes. So an alternative suggestion that many of us have worked on, including my research group, is that perhaps from the get-go, it's a very natural explanation, that perhaps from the get-go you could make seeds that were much more massive. Could you make seeds that were 100,000 times the mass of the sun rather than 10 times the mass of the sun, which you would get from the end product of a star? And so then the idea is, what is the kind of physics that is needed in order for a black hole to form so rapidly to such a high mass from the get-go, very early in the universe? When you work out what conditions you need, so basically what we need are conditions, rather like the water that is falling into your bathtub. When you lift the plug, you have this vortex, and your water funneling in really rapidly. So what you need is gas funneling in very, very rapidly in the early universe, making it to the center of a galaxy. But the galaxy has not assembled yet. So what you really have is just gas. No stars have formed. So the idea is that these are pre-galactic black holes or direct collapse black holes. And it turns out that the conditions under which this can happen are ubiquitous in the early universe. So this can happen. But the question, of course, is once matter goes into a black hole, there is no information about the initial conditions. So looking at the black hole at the center of the Milky Way today, we cannot tell whether the initial seed was a wimpy seed or if it was a very massive seed.
Yes, yes.
So the only possible indication you could have is by looking at the environments when these seeds actually form, so very early in the universe. So that's when you would have some inkling of how the black hole assembled. If we caught it in the act of assembling.
Okay, but a major thing is they didn't come from stars necessarily. Right. We have been taught, I mean, we've been prejudiced to certainly believe that it started with stars, these individual stars. They collapsed, you get a black hole, eventually you get a galaxy, but you're saying no, it could start in this other way. So that is certainly interesting. The other is, I guess, that they're all over the place. They're in every galaxy.
Pretty much. But you know, they don't actually have to form in every early galaxy because galaxies in the universe grow by merging with each other.
I see.
So it turns out that even if you seed 1 in 5, 1 in 10 very early on in the universe, as a result of merging over cosmic time, you could end up with one in the center of every galaxy like our own.
I see. Okay, now we've got that part out of the way. Then in terms of other areas of your own work, should we talk about the lensing?
Oh, absolutely. But before that, you know, the question is, it's all great to have these theoretical ideas, right? So what is the observational evidence? Where is it going to come from? So it's James Webb Space Telescope, which is a satellite that is going to be a telescope in space that's going to be launched in 2018, is going to access. So it has cameras that are sensitive in very long wavelengths, which is the infrared. And you know, in the universe from early times, light gets stretched to longer and longer wavelengths as it comes to us. So the longer we are able to detect wavelengths, most sensitive detectors that we have, the further back in time we can go.
Yes.
And so this telescope has instruments on it which are going to be sensitive in the right wavelength range to detect the first growing black holes.
That is amazing.
Pretty exciting. And so, you know, we may well be able to settle the question. I mean, I think in nature what probably happens is you probably form black hole seeds both ways. I don't think it's one or the other. But the question is, the most massive black holes in the universe probably require these very massive seeds from the get-go. And it would be very nice to catch one in action.
Right.
As it's growing.
I think everybody is in this field must be very excited to wait for the Webb to go up. That's such a thing. The Hubble has done incredibly.
The Hubble, and you know, coming to gravitational lensing, right?
Yeah.
So a lot of the work that I do would not have been possible without the Hubble Space Telescope. We need the exquisite resolution of the Hubble Space Telescope to actually detect these gravitational lensing effects.
Let me clarify that you wouldn't have been able to do this with optical telescopes on Earth.
We would have found these distorted images, but they would have been fuzzy. So you wouldn't have been able to do the kind of science that I'm doing with them. So for example, the cluster of galaxies, which is sort of in the foreground, has a huge amount of dark matter. And it turns out now we know that it contains dark matter, some of which is smoothly distributed, some of which is clumpy, and it distorts the shapes of galaxies that lie behind it. So when we look through, a galaxy which is, say, normally projected on the sky, looks like a little circle, gets stretched out if light actually passes through regions of space-time that have a huge pothole generated due to dark matter. So the presence of dark matter causes huge bumps in space-time, and light travels along space-time follows that pothole, and so we end up seeing a very, very distorted shape for a galaxy.
And I believe in your book you have images of this as well.
There's these dramatic images.
Just,
and what is very interesting is because sometimes these potholes can be so deep that you can have a beam of light and that comes through and it actually gets split. So you end up seeing multiple images of the same object.
Two, but multiple.
Multiple images of the same object. And in reality, you have only one object in the universe, but we see copies of it.
Yes.
And these copies are very, very interesting to detect because they offer us important constraints on modeling. So what we do is we look at these distorted shapes and we back out the amount of dark matter that's actually causing these deviations. And so we're able to map the dark matter. So the more detail we can get out of Hubble Space Telescope images in terms of the distortions, the better we can actually map the dark matter. So for example, now we have the latest data from this project called the Hubble Frontier Fields Project, very deep look at 6 clusters. And we've reconstructed the dark matter distribution in those 6 regions. And what we find is we can look at the reconstruction that we have, compare it with theoretical predictions of the dark matter theory, the cold dark matter theory, which we can compute using simulations, giant computer simulations. So simulations that mimic a small slice of the universe. And so then we can compare regions, clusters that form in our simulation with real clusters. And what is amazing is it's an exquisite match to the theory. It's an exquisite match to the theory. This is what is so troubling about cold dark matter, right?
Yeah.
So if you look at a lot of the observational data, you look at a theoretical understanding, everything fits rather nicely. There are a few gaps here and there, but that could be our own limitation in terms of the accuracy of measurements and so on and so forth, and lack of understanding of some physics of galaxy formation. But by and large, things fit very, very well.
That is amazing.
The awkward, embarrassing thing, of course, we keep coming back to this, we don't know what the particle is.
Whatever it is, but
right.
It shows up really well.
Yeah.
You do really sophisticated modeling and so on too. I don't think that kind of thing is as familiar with us, but you mentioned big data, which is a big thing, and your ability to really check, you make a model and then you really check it with these, with what you find. What's happened with that? How has this evolved now?
Yeah, so I think what has been pretty incredible is the sophistication both of our understanding of the physics and mathematical techniques that we have, so sort of the paper and pencil theoretical work that can be done, as well as the sophistication in computing that actually allows us to render our models and change and perform experiments, if you will. I want to come back to the point I raised earlier. One of the limitations in cosmology has been that we have only one universe in which we're making these measurements, and we can't do controlled experiments. So you can't do a randomized controlled trial, and so, but we have something that is very similar, which is that we can now in a computer simulate with a bunch of initial conditions and instantiation a version of the universe. And then we can change the initial conditions and we can rerun the simulation and produce another piece of the universe, another chunk of the universe. So it kind of allows us to produce a sample of universes to test observational data with. But what is really sort of problematic about this is, is sort of from the epistemic point of view, is that you really are getting out what you're putting in a way, right? So I can pick properties for the universe, initial properties, and then I can let it go. I can let gravity do its trick and run it for 13.8 billion years and look at what a slice of the universe should look like today. I can change the initial conditions and I can rerun it, right? But I still am constrained by what I put in as initial assumptions, right? So this is very tricky in science vis-a-vis the scientific method. Because if you look at experiments in chemistry or biology, what you do is you have a specimen, you manipulate it, you change conditions of, temperature, salinity, pH, and you look at how the sample evolves, changes, and you can make a record, and then you understand it, right? So you are actually inferring by doing a whole bunch of independent experiments, right? So we don't have that power in cosmology yet. We've devised these wonderful technique of cosmological, large, sophisticated simulations that allow us to sort of mimic the universe and make measurements. So we make these mock measurements in these simulations, and then compare that to real data to see how well the correspondence is. And given that we have this scheme, as I said, this cold dark matter model works incredibly well, both on galaxy scales, on cluster scales. And the only sort of places where there's a little bit of tension, and the tension is really about the detailed understanding. It reflects our lack of understanding of the physics of star formation, which is a very complex process.
So I hear.
It's a very complex process.
It's one of the hardest problems in cosmology, apparently.
Absolutely.
Why? Is it because of the cold gas and what?
Well, so, I think the problems that are the hardest to crack are the ones in which you have to integrate sort of small scale behavior and larger scale behavior.
I see.
So there's a what we call technically is a challenge of the scales, of physical scales that you need to resolve. So for example, in a simulation, for example, to form stars, you would not only need to understand how individual molecular clouds interact, but you would also need the entire cosmic context of where in a galaxy this star-forming clump is sitting that is composed of these molecular clouds. And so you would need to model the large-scale flows of gas in the universe, the dark matter network, as well as the detailed physics and chemistry of the molecules in those clouds. Because, ultimately what really you need to model is the cooling of the gas, the clumping of the gas, and the gas needs to become very dense. It becomes cooler and denser and denser, and then it forms stars. Whereas the gas that is on cosmic scales is not dense at all. It's a very, very low density gas. So to be able to, in the same calculation, zoom in on where all this action is happening on small scales, and then zoom out to see the context to get it right, is a huge challenge.
That's very grateful for that explanation.
No, but you have the same kind of problem even, in actually, although I sort of talked about how gas makes it to the black hole, it's the same problem for understanding how gas actually flows right into the black hole.
So there's a problem with just understanding this gas motion, I guess, and I should say dynamics.
Dynamics
of the gas
and the scales.
In this huge, huge universe. It seems to me that the work that you do requires, because of the dark matter in particular, where we're talking about a particle, that there is, I don't know whether the word is convergence of the largest scales in the universe and the smallest. I don't know if it's all the way to quantum, but you're dealing with this enormous stretch. Is that true, and what does that do to your thinking? Because in old times, they didn't have to do that.
Right. So I think that it's absolutely true that, in a way, the way to tackle these problems is to kind of synthesize what's happening on many different scales. And so, there are techniques that we kind of partition the problem and we try to do it and then patch the solutions to get sort of a more synergistic understanding. And yes, that there is actually no escape but to do this.
That's tough.
And in a way, I think that what is nice about tackling these huge scales, for sure, is that you realize how significant and insignificant we are as humans, right? Doing this. So we have this cognitive capacity to make sense of all of this, which is incredible. But on the other hand, there are limits to our understanding. So some limits come from our actual innate capacities. The other limits are limits that we impose as human beings, on our psychology, on how we think, our beliefs, and so on. So I think, so working in cosmology really gives you a humbling view.
I was going to say,
of
that's
the universe and of
day.
ourselves. Of ourselves.
Every day,
of ourselves.
right. I wonder if there's a space for a really big ego. I would think that every day this would, yes, well, in spite of that, you get some big egos.
I think there are
Exactly.
plenty of big egos jostling around.
Exactly,
Yes.
exactly. We are about out of time, but I'd like, as just a finishing statement from you, is what do you think is, say, one or two of the biggest issues today in cosmology, where we're going and so on?
So I think that the figuring out the nature of dark matter and dark energy, I think, are the big open questions. And
you picked the hardest ones.
Right. And I think that, aside from that sort of understanding the inventory, so for example, our current understanding is that the universe is also replete with black holes.
Mm-hmm. Yeah.
So the recent LIGO discovery of the collision of stellar mass black holes is incredible, right? I mean, delighted to be alive when this happened.
Yeah, right.
However, all the work that I've been talking about on larger scales, we actually expect supermassive black holes to be colliding too. Mm-hmm. And the gravitational waves from those collisions are at much lower frequencies. So we need instrumentation actually in space, something like LIGO, but in space to do that. And that's afoot. So that project is called LISA. Yeah. And there was a prototype that recently was sent up, and it actually performed better than expected. So that we don't have a technological hurdle anymore. So I think, there are many windows that remain to be opened for us, that will explain to us what the dark matter particle might be. So you never know, there may be an experiment, a direct detection dark matter experiment that might yield a result any day now. Or we have all these large astronomical surveys that are being done to really pin down when dark energy takes hold in the universe and starts to dominate. We know that dark energy is dominant today. It's a dominant component, and it is driving the accelerating expansion of the universe today. And we know that it probably picked up about 7 to 8 billion years ago, and we want to really understand that in order to figure out what it could be. So the current understanding is that it could be maybe some kind of energy that is associated with space itself, so kind of vacuum energy, and it could have been generated by some fields very early in the universe, et cetera, et cetera. So there are sort of many models in play. We don't really have a leading model actually. And so we need a lot more data to figure out how to construct a viable model. So I think all of these big questions stand to be answered, or at least exciting developments in the coming decade or two.
And it sounds as though you're optimistic that you actually are going to be able to identify some of this.
Absolutely,
just,
absolutely.
What an
I'm very
exciting
optimistic.
thing.
Yeah,
what an exciting thing. I wish we could talk longer. I really appreciate your coming and giving us all this wonderful information.
Thank you so much.
Please write many more books.
Oh, thank you. No. And I think, one sort of reason I really wanted to write the book is that, much as I am optimistic about the science, I've been slightly pessimistic about the misunderstanding of science, the distrust of science, especially in American society.
Especially us, yes.
But I really do believe there too that part of that mistrust and disbelief comes from the lack of understanding of the process of science, of how actually science works. And in particular, I think the two issues that the public has a lot of difficulty with, and as we saw even scientists have difficulty with, is the provisionality of science. The fact that you have to be nimble and ready to change.
A whole new mindset.
Oh yeah, and you have to be open. You have to be open.
Absolutely.
And then understanding uncertainty and risk. And I think evaluating that, because that's where where science and society collide, right? So sort of policy issues and understanding future risk and uncertainty and how that plays out, and how as our understanding gets more refined, we get a better estimate of the uncertainty and the risk. I think the fact that one has to always stay open to changing one's mind, I think is very difficult, because the pace of change, pace of technological processes, progress has been so rapid in the last 50 years that I can understand why it's a challenge. But I really think that having the process of science kind of unraveled demystified would go a long way in sort of helping with that.
I agree, and certainly young people coming up today are more disposed to this. They're not locked up in little villages all over the world, which is our, centuries and centuries people were,
Right.
and locked into a particular worldview, so that this is changing, and then people discover, hey, this is really neat. You don't know what's happening next.
Right, right, absolutely.
This is exciting.
And I think, partly
scientists live for it.
The image of science,
Yeah.
it's the image that we've presented of science is a very sanitized, kind of
Yeah.
sort of, objective people, extracting these truths from nature or
Yeah.
whatever. So I think a lot of these misconceptions about science, when they are clarified, I think, hopefully people will understand how wonderful science is as a method to make sense of the world.
Well, you made a great contribution.
Thank you so
with your
much.
book.
So
Thank
delighted
you
to be
very,
here.
very much
Yeah.
for joining us and for giving this wonderful information. Thank you.
Thank you.